Oh, you're giving me control this week? Okay. Hello, and welcome to week 2 of Programming Quantum Computers. And this week I have the privilege of trying to work through new things that make my brain go a little screwy. So that's what we're going to be doing today, is looking at some of the things in chapter 2. Let me share my screen, and then we'll just head right on out. And feel free to ask questions at any time. I know kind of the initial part, probably not a whole lot to, I won't say talk about. I'm going to be showing things that helped me understand it. And then definitely once we get to the end, everybody's favorite problem, the last example, we'll have a lot of discussion there. So let's go ahead and get through some slides. Just a little about me. I introduced myself a little bit last week, but a little more detail. I've been a developer since 2000. So that seems like a long time ago now. And I've worked in corporate environments, in startups, doing contract work. So a lot of fun stuff in different places. These days, I'm in the developer training space. So in-person training, workshops, conferences, speaking at conferences, doing videos. I have a course on Pluralsight that I'm actively working on updating right now. And online, I'm Jeremy Bites. So if you're ever interested in looking for stuff, I'm primarily in the C# world these days. That's where all of my stuff is Jeremy Bites on YouTube and on the web and on Twitter and all those other fun places. So chapter 2 is called 1 qubit. And I'm glad it's called 1 qubit, because once multi-qubits start happening in later channels or later chapters, it starts to get a bit more confusing. So we'll start small. And kind of the big sections in this week, there's an introduction to the circle notation, a lot of the initial QPU operations, and then there's a spy hunter example, which shows a way that you can have secure, well, I'll say, you can tell if your communications are insecure. That might be the best way to understand it. It doesn't necessarily give you secure communications, but it lets you see if somebody's listening. So I'm not going to go into a whole lot of detail, because I'm going to be kind of showing things in the QC engine simulator, because I found that that was really helpful to me. I've been doing classical development for a long time, so my brain is used to thinking in, okay, if you do this, the computer does that, and it will do it the same way every single time you do it. And quantum isn't like that. And it's about probabilities and other things that makes me uncomfortable. But so I've been doing a lot of, let's try this out and see what it does. And the circle notation, even though it's a little, I won't say it's simplistic, but it's limited in what it can show, I found that it has been pretty useful. And so looking at, here's just a few examples that are in the book as well. So the 0 example where the first circle is filled in, the 1 example where the second circle is filled in. The third one that we have here shows a 50-50 probability. So it might be a 0 or it might be a 1. We don't know yet. And then there's also phase operations, which I'll be introducing this week, but basically what's part of the introduction is that phase operations don't really affect a single qubit. So chapter 3, when we're talking about multiple qubits, is when those will start becoming more important. So yeah, so we'll be seeing this notation as we go. So let's just look at some of the operators, and I'm going to be going back and forth on the simulator to kind of show how this affects things in code. So not is an inversion. So it's going to flip your 0 circle and your 1 circle. And it looks like Nuri just joined us. Hi, Nuri. Welcome. Let me flip over to the simulator. And what I have here is a not. And so the code, this again is JavaScript code. So the first line actually creates our 1 qubit. The second line writes a 0 to it. And then we do the NOT operation and then the read operation. The thing that I really like about this particular simulator is that you can click through it and it animates based on what the operations are doing. So I've already run this program. I'll click it again. This is actually a deterministic program because we're not doing any superposition operations in this one. And I like that you can put the, I don't know what you call this, a cursor. It's not really a breakpoint, and I'll show why it's not a breakpoint. As a classical developer, it makes me very uncomfortable, but we'll see that in the next operation. And so here I can see when I writing a 0 doesn't really change the circle notation at the bottom because it kind of is a 0 to start with. But watch what happens when I click on the other side of the NOT operation. The circles actually animate. And that was really, really helpful to me to watch these circles flip back and forth, because now it's showing me, okay, here's how these things interact, and here's how it works. And then the read operation, which again, this basically flips the circles. And so we don't have any superposition here. As soon as we do the NOT, we can see the second circle is 1 filled in 100%. So we have 100% probability that this will actually be that it will be a 1. Now, NOT is a reversible operation. I'm going to be noting, and it's actually in the slides, which of these operations are reversible or not. So if you do a single NOT, it flips the bits, or qubits, I should say. You do another NOT, it flips them back. So it is actually reversible. And some of these, whether they're reversible or not, becomes very important. So NOT is pretty comfortable because it's pretty similar to how classical programming works. When we don't have any superpositions, it does things that feel very comfortable. But the next step from there is actually dealing with superpositions. And this is where it took my brain a little while to wrap around this. And this is the had operation. I pronounce it Hadamard. I don't know if there's another way of pronouncing that. I haven't heard someone say it, so that's how I'm going to pronounce it. And what this does is it puts the qubit into a superposition, which is, we don't know what its current state is. It could be either a 0 or a 1. And the way that I think about this is it's really like a coin that you flip while it's in the flipping state. So you flip a coin, and while it's up in the air doing this, that's in the had superposition. So we don't know what it is. And in fact, it's neither or both. It's a possibility of something that might happen. And it's not until we actually stop it and read it that we see what the actual value is. Now, the thing that I find interesting about had is that it is reversible, meaning that if you do 2 had operations together, you get the original value. So why that's interesting to me is you think of, okay, I do a had, I flip a coin, the coin's in the air, it's spinning, I don't know what it is, and I can unflip it and put it back into the state it was before. And that, again, it has no business in reality, but that's the way my brain is processing it. And my brain is okay with that. So there's really kind of two things that we can do basically, unless we add other operations, is we either flip the coin, look at it, which collapses the superposition so we get the actual value out, or we can unflip it and put it back into the state that it was before. Again, not dealing with putting other operations in between right now. And so read is very important in this world, because a read is going to collapse the superposition. So if we have something that's in a had state or a superposition that has probabilities of some kind, it may be this, it may be that, we don't know, then as soon as we read it, it's going to collapse that and give us an actual value. Now, this is not reversible. Once you read a qubit, you can't unread it, meaning you can't put it back into the same superposition state that it was in before. After you read it, if you decide, hey, I'm going to put this back, I'm going to put this into a superposition, it's a different one. So once you read, it's like looking in Schrodinger's box. Is the cat dead or alive? Well, as soon as you peek, and you can't undo that. There's a little note down here, which as a classical developer, this bothers me in the simulator. And I'm going to show this rather than talk about it. Okay, so let's, is this big enough for everyone? Okay, I tried to make it nice and large. Okay, so let's do a had operation with a read. So again, kind of this output, when I run the program, not real exciting. Okay, I got a 1 out. If I run it again, I may get a 1, I may get a 0. To me, the running of this is not very interesting. To me, what's more interesting is, again, kind of clicking through to see what happens. Because, so we write the 0, and then we use had to put it into a superposition. And now we can see in our circle notation, we actually have a 50-50 probability. So this qubit, if we were to read it right now, 50% chance of being a 0, 50% chance of being a 1. And then if we click past that, in this case, it says it's a 0. The thing that bothers me and about kind of this simulator and clicking through, and I'm assuming that this is true of real quantum computers as well, is since after you read something, you can't unread it. If I click back, then even though it's showing this is in a superposition, it's not the same superposition. So I don't hit this green run program again. But if I just click back and forth between reading and unreading this, you'll see sometimes I get a 0 and sometimes I get a 1. Now, as again, primarily a classical developer, this really bothers me, because one thing that I was trying to do, I found with the more complex operations, such as the spy hunter example that we'll see later, is I wanted to kind of keep clicking it until it said, hey, here's the result that you were looking for that happens 1 out of 50 times. And then I'm like, okay, well, now that I have that, let me kind of trace through the application that got me there. And you can't do that. That really bothers me, because every time I basically kind of try to trace through this application, it's going to be different. So there's really no way to say, oh, well, what was the state at this point in time? I mean, I can tell it's in a superposition, but I can't tell what it's going to collapse into because it's non-deterministic. So that's kind of bothering me, but it's something that I've kind of had to try to come to grips with. Now, as I mentioned, had is reversible. So if we do 2 hads, then it will put it into a superposition, and then it will collapse it, or I'll say not collapse it, actually put it back to where it was before. And then if we read it, we have 100% chance of this being a 0. With the write operation, I can say, okay, well, let's start with a 1 and see what happens. And it's the same thing. So I put it into the superposition and then undo that, and I will always get a 1 out. And so even before I read it, according to the circle notation, I have 100% probability that I will get a 1 out of this. So again, the had is 100% reversible. You can unflip the coin that is currently flipping. However, if you put a read in the middle of this, that just changes everything. And you'll notice I actually like the way that the circuit diagram does this. Is after you do the read, it's basically there's a break. It's not even a continuous line that goes past the read. It's almost like, okay, you're done with that. We're starting a new qubit operation from here forward. So we have, it's like, okay, we'll start with this 0 state that we got out of this, but going forward, We're going to be not thinking about any of the stuff that happened before that. Does that make sense? So again, kind of clicking through this simulator was really, really helpful to me to see just kind of, okay, well, if I put a knot in, see knot, oh, okay. Then I can see the 1 and 0 circles flip in the circle notation, even if they're in a superposition, and then read them out and all of that. So I have found kind of clicking through to see how the circle notation is affected to be really, really helpful. Can
Jeremy,
you hear the
I think
dogs?
the read may have introduced some of the randomality on the had read, on the not and had and dehadding it, because read itself is the one that gives you sometimes random output.
Well, the read will collapse it.
Right. So it has a potential of generating a reading that is not what you thought or expected going into it. So when you were going back and forth and saying it bothers me, I'm wondering if that's because of the read, or is that because of the quantum nature of what occurred before?
I think it's actually, this is interesting. Oh, okay, I got a 0. It might be a quirk of the simulator. This might not be how, well, I don't even know. Does anyone know? Can you step through a running quantum program? I'm kind of guessing you can't. So this may be,
So I'm going to just jump in
okay,
here.
good, Linda.
So the read is deterministic. You get one result.
Yes.
The had is non-deterministic, even though it looks deterministic because it's got 50-50. Because we're not getting the full measurement, because the little lines that that are shown there, they have some impact on the measurement. We're not talking about that yet, but the had is non-deterministic. The read, like Jeremy said, collapses it into an outcome, but it's the outcome of the had. So I don't know if that distinction is what makes sense. So that the read result will change, but the result is the output of the had. So it's the quantum operation that's non-deterministic. Does that make sense?
It totally makes sense, except that the text in the book says the read operation is a formal expression of the previously introduced readout process. Read is unique in being the only part of a QPU instruction set that potentially returns a random result.
Yeah, but not to put too fine a point on it, the random result from an operation that is non-deterministic, which is the had. Because if you have a not and a read, then it's going to be deterministic, because as Jeremy started with, but it's the quantum operation that's the non-deterministic part. So it's a good distinction. But again, I'm no expert here. Okay, this is just the way I'm looking at it. But as we look at superposition, and then as we get into more qubits with entanglement, it's the quantum processes that are probabilistic. The knots and the reads, they get the value when you implement the quantum function, if you will. I don't know if that's making it more unclear or what, but that's the way I understand it.
Yeah. So as Lynn said, if we go back to the example without the hads, when we're just looking at the knot, this read is always, in this case, it's always going to read a 0 because the input is a 1. So again, initial circle notation is 100% probability. If you read this out, you will get a 1. If you say not, it'll flip those 2 circles. Now we have 100% probability that if we read this out, we will get a 0. So even though we technically don't know what it is until we read, since the state doesn't have any superposition or quantum hoo-ha going on, hoo-ha, a technical word, this, even though the read is based on what's coming before it, based on the probabilities, this is always going to be the same every time we run this. My brain really hates this. So I probably should have reordered these since I've kind of shown them a lot. This is just the order that the operations are in the book. So a write will write a value to a qubit. This is also not reversible. So if I did have something, let's say I had this in a superposition, and then I did a QC write 0. Let's get rid of the not and read. Oop. So basically this had operation gets destroyed, ignored, skipped. The write will, just say, okay, this is now a 0. So that is non-reversible. You can't, in this case, you couldn't unwrite in order to put it back into the superposition state that is immediately before the write. So that's why I have this down as not reversible. So just like a read, once you read the value, it collapses the state. You can't put it back into what it was before. Same with a write. If you write to a qubit, you can't put it back into the whatever state it was before. So non-reversible. Now phase is fun because I don't have to talk about it too much because it, as the 4th bullet point says here, it doesn't really have any effect on single qubit operations. And since today's chapter is called 1 qubit, I don't have to worry about it. But I do want to talk about what it does because I ran into some interesting things when I was because I've jumped between the QC engine simulator that was written by the book authors and the IBM composer, which will let you use a simulator or a real quantum computer somewhere in the world. And the terminology is a little bit different in those environments. So first of all, let's do a phase and just kind of show what it does with the circle notation. So in the world of the QC engine, the phase takes degrees as a parameter. So if I say phase 180, it's going to do 180 degrees. And in this case, it's, let me click before it. So if we look at the circle notation, we can see we've got the line going straight up and down now. And then if I do a phase 180, now it's flipped around and it's pointing in the other direction. And then we can have different values as well, which here's a 90, for example. And this is 90 degrees. These are relative to each other. I'm going to stick a hat in here, which isn't necessarily a good thing in this case, but just because if a circle doesn't have any probability, you can't see the lines, if that makes sense. Actually, I'm going to set this to a 0. We'll start with this state. Okay, so let's walk through this program where I write a 0, then I put it into a superposition. So we can see we have a 50-50 probability, again, between the 1 and the 0, but both of the angles are pointed straight up right now. If I do a phase 90, now these are, the 90 degrees is referred to as a relative angle. And so now, the straight up and down versus the one that's going this way are 90 degrees from each other. And something that's noted in the book that I have found isn't always true in the simulator is that it mentions that generally with the circle notation, since it's a relative angle, at least one of these will be pointing straight up since they're relative to each other. So like this is the same as this, if you watch my fingers, because they're still relative 90 degrees to each other. But for notation purposes, there's usually one that's pointed straight up. I have found that there's some scenarios where they go like this or like this, And I don't know if that's in my examples or not. So sometimes the circle notation that comes up in the simulator doesn't necessarily match what the book says. Hey, this is the way you should do this. Phase is also reversible. So you can apply a negative angle, phase negative 90 in this case. Okay. I can type properly. And let me put that hat back in, because I want to see the lines on both circles. Okay. So if I say 90, then it flips the 1 bit flips one way. And then if I say negative 90, now it's back to the state it was before. So you can undo a phase operation by using the negative angle. One thing that is in the book, but is kind of skipped over, is that there's other names for common phases. So in the book on page 7, there's actually a chart that says this, but I kind of didn't pay a lot of attention to that chart because it didn't mean anything to me when I was on page 7. And then later on, I was in a different environment and I'm like, what's an S? I don't know what an S gate is. And if you look in the index, there's no S gate listed in the index of the book. So it was a little frustrating. But on page 7, it notes that a phase 180 is also referred to as a Z gate. 90 is referred to an S gate, and 45 is called a T gate. And again, the environment notes that I have here, QC engine uses the angle, so it uses the degrees. The open QASM uses the ZST notation. And then if you do an angle other than one of these, it uses radians with pi, which is fun. So, yay, math. Let me just flip to the IBM environment for a second, just to point to these things. This is actually the teleport test, which is from chapter 3. So we're not going to go through the details of this. But when I was going through, again, you can hover over and it'll tell you what these are. So an H gate is a had operation. There's the NOT gate, the C NOT, the CC NOT, the TOEFL gate, which are not in chapter 2. And then when you get to here, it says T gate, it says S gate, it says Z gate. And this was part of it, and I was going back and forth between the QC engine with the JavaScript and this open QASM. And so it took me a while because even when I look at the code, that's this line of code, line 12, which is a little small, but it says T. So I'm running a T operation. So it's not even like it's giving me a detail about it. So this was a bit frustrating to me initially trying to figure this out. So that is why I created a slide about it so that I don't have to worry about this. And hopefully you don't run into the same fun stuff that I ran into with the notations. Okay, there are other ways to turn your circles around. Our circle notation only shows one axis. But you can also, these are rotate operations. You can rotate on the y-axis or the x-axis. I'm assuming that means that the phase we've been doing works on the z-axis. And this is not something that is visible in circle notation. If you're doing these other angles, you can't see it in the 2 dimensions. You really need the 3 dimensions. And again, as Lynn showed last week, that's one of the kind of cool things about the IBM simulators. It has the Q sphere with this, I think it's called a block sphere, that you can actually see the different angles on. I'm wondering, okay. And then Lynn also showed this does have an inspector where you can step through. I was so excited when she showed this because I didn't think this had it. And so if I, let's come to this one. Step, there we go. Now we can kind of see that these are probabilities of what our result might be. And there's kind of a circle notation here where if you hover over it, you get all of this nerdy stuff, which I do not understand yet. And hopefully I will learn this at some point. But this is basically a circle notation along the left-hand side here. And then because this has 5 qubits actually in operation, 2 of them aren't being used. But then the sphere actually shows, okay, well, here's all of the angles. So we can see that they're not, they're going through the various axes. Again, I don't know exactly how to use this other than it's kind of cool. I'm going to leave that to whoever has to do chapter 3, where we start talking about multiple qubits. Okay, let's see. And then there's R naught, which is a root of naught. And this is the idea of it's a square root of the naught operation, meaning if you do it twice, you get a naught. Let's just do this. Okay, so QC naught, R naught. Let's do R naught. Okay, I obviously turned off my insert at some point. There we go. R naught is not a function. Oh, yeah, because it's called root naught. There we go. That's better. And let's see if we can. Okay, yeah, here's the relative angles that go. I knew I didn't make that up. So starting with a 0, the root of naught puts it into a superposition where it's not just, so we can see the circles are smaller, so it looks like a 50-50 probability, but then the angles are also pointed at each other. And that looks like it's actually, it should be a 90 degrees based on, phase 90, which I'll show that in just a second. And if we do a root naught twice, then this is the same as doing a naught. So let's see. Unfortunately, the circles don't animate the same way. But if we do let's do a QC. Yeah. I'm just going to comment stuff out. So again, a naught turns our 0 into a 1 by swapping our bits, our circles. The root of naught does it halfway, I guess is the best way to think about it. So that if you do it twice, then you get a full naught. But if you do it once, then you get this superposition state. And I'm not sure how this is useful because, again, kind of as we go later into the programming where we're actually using these operations, that's where I'm really hoping that it makes sense for why I want to do this. But in the meantime, I have this root of naught, which if I do it twice, I get a naught out of it. I'm assuming you don't normally do it twice because then it wouldn't be very useful to do it partway. So that's the R naught. And in this case, I put it's not directly reversible, meaning I can't really undo an R naught operation. But as we'll see in just a second, you can reverse it with a little bit more ingenuity. So let's look at that, because there is also a section on combining operations, or it might be called decomposing operations. So what we can do is we can take 3 operations and stick them together, and they do the same thing as another operation. So in this case, this first one, a naught is the same as a had, a phase 180, and a had. And this is where I kind of went to town with the simulator, trying all of these out. Okay, so QC naught. We've seen this several times, so we know what it does. it will flip our circles. And so according to our chart, if I do a QC had, a QC phase 180, and a QC had, then this will give me the same output as a not. And it actually does. So, and again, this is something where right here, before I do the read, I have 100% probability of reading a 1 out of this. So these three operations, so had phase 180, which, you see the little arrow flip around on the 1 bit, and then unhadding it leaves us with a 1. And this will do this every single time. So starting with a 0, had phase 180 had, I'm going to get a 1 out. So even though the hads are non-deterministic, we're basically, again, kind of flipping the coin and then unflipping it by doing the 2 hads. But by sticking this other operation in the middle, we're changing the state. So again, brain really kind of hurty when it comes to this kind of stuff. But so these are decomposable. And the same thing, oh, look at that. I have a really bad typo there. Let me fix that. Oh, except not there. Here we go. Okay, it's not a terrible typo, but it should be 180, not 190. So we can take a phase 180 and decompose it to a had not had. And what I find interesting is we can take an R naught, and that's a had phase 90 had. So if we think about, okay, we do an R naught twice, and it's the same thing as a not, we're basically kind of doing a phase 90 and another phase 90, which gives us a phase 180, but kind of with hads mished around in between it. So it's, kind of half of a not. So this is actually helpful, seeing how something can be broken down into a phase, because now I can see, okay, well, phase 90 is half of a phase 180 as far as the relative angles are concerned. And then I can also see that I mentioned that R naught is not directly reversible, but I could use this decomposed version of R naught to say had phase negative 90 had, which will put it back the other way. So you can kind of reverse an R naught, but a little differently. Does that make sense? And I'm pretty sure I tried that. As I'm saying it, I feel like I made that up. But I'm pretty sure I did this. Okay, so
it makes sense because the 2 hads next to each other kind of cancel each other out. So it's really just had 90 phase.
Let's
and
see.
Another phase 90.
Yeah, so in between the hads, so actually in between these hads in the middle, so doing the first 3 operations, that's the same as an R naught. So this diagram, I'll say it looks similar. It's not quite the same as what we saw earlier. And then if we click through this again, do the negative 90, now we're back to where we were before. So you can undo an R naught, but not using an R naught operation. So that's why I said indirectly.
But to Carl's
reversible.
point, the had on line 6 and had on line 8 perform a identity. They should be removable without damage, which would put a not next to each other from line 5 and line 9.
Well, what this would end up
Again,
doing, if we did this, is we do a had, put it into a superposition position, apply a phase 90, and then phase negative 90. So basically do the phase and undo the phase, and then the had again. So yes, I see what you're saying.
So what I'm saying is that the transitive commutative pencil pushing of symbolic math here could or may lead us to understanding how to manipulate formulas, because
I'm
those substitutions let us freely substitute a symbol for another set of symbol, which is what you do in symbolic logic anyway, and then push pencils around from the right to left and so forth,
mhm.
cancel terms, and you end up like, aha, that's my proof.
and that's excellent, an excellent point, because I've actually found the circuit diagrams to be more useful than the source code, because again, as a programmer, I'm thinking in code that my brain knows how to interpret. This is code that my brain doesn't know how to interpret yet. Hopefully it'll get there. But the circuit diagram is something that is symbolic, that, like Nuri was saying, we could potentially move things around. I do want to point out one other thing. And that's actually another reason why I find the IBM simulator to be interesting, or I'll not the simulator, but the quantum composer, because this is all drag and drop. So I can build a circuit if I wanted to add a knot. I can drag it and drop it where I want it on my circuit. And I don't have to worry about writing the code. It takes care of that for me. And you can delete them with the delete button. So they can go away. So I think that the IBM Composer will be more interesting to me as I start building my own custom circuits, beyond the, okay, I have a phase and another had. The one other thing that I kind of want to point to that I found interesting, because, and this actually goes to the next point, which is the Spy Hunter example. So I loaded up the Spy Hunter example in the IBM Composer, and then I ran it against, I believe it was the Santiago, IBM Q Santiago. Oh, wait, that's not the right one. Go back to my jobs. There we go. So I ran it against IBM Q Santiago and I got an error. So it actually didn't work. And the error I got was instruction bfunc is not supported. Well, I went through my entire code. This is the code that came with the book. I did not write any of this. And there is no bfunc operation in here. So one thing that was interesting is I clicked on see more details. And one of the first things that the IBM Composer does when you go to run it is it transpiles the circuit. So it turns the circuit into something completely different. And just looking at it, so I haven't studied this. So the had operation that is right here actually gets turned into these three operations, which is an RZ, which I'm assuming is a rotate Z. I'm not sure what the root of X is. I don't know if that's an R naught or something else. And then it does the same RZ operation again. And if I looked at the value, it's actually an RZ and the value is pi over 2, which is 90 degrees. So even like a had operation gets transpiled into something that the IBM quantum environment can understand that's a little bit different. So I just found that interesting. And I couldn't figure out why it didn't run. So, okay, now that I've used all of our time, the last thing, which is the Spy Hunter, this is probably what we should have spent the whole entire time on. So I'm going to give my interpretation of what this particular demo is saying, and then we can discuss. So this particular demo, the way that I understand it is it's trying to show how we can tell that there's a man-in-the-middle attack in our communication. So, but it's probabilistic, meaning we're not going to know 100% of the time. And I believe that according to the text, it said based on just this particular code, because there's a lot of bits that aren't great about this code as a way to communicate between two people. There's a 1 in 50 chance that we will actually detect that there's a spy in the middle, because a certain set of things have to happen in order to get that. And the probability of that happening is 1 in 50. And the program's written so that there is always a spy in the middle. There's 100% always a spy in the middle, but we only know about that 1 in 50 times. And so the way that I'm interpreting what this type of code is useful is if we do this over a range, and this is actually one reason I wanted to run it on the IBM environment, because it actually will run it 1,024 times as the default and show you the outcomes of each of those runs. So you could actually see, here's the actual probabilities of each of these states happening. And I'm still going to work on that. I'm going to figure out what's wrong, or it says maybe try another quantum environment or simulator that supports this function. So I have more research to do on that. So the reason why this isn't a great example of Alice communicating with Bob is because Alice is doing 2 random things at the beginning, and Bob is trying to guess what those 2 random things are at the end in order to get what Alice sent him. And the chance of, those 2 random events lining up is slim. So as a communication channel, the way this is set up, not real great. Now, I could see how if there was a tertiary channel and Alice said, okay, here's the initial states that I'm sending you for the bits so you can read them, so that you can read them with 100% accuracy. And if some of those bits on Bob's end don't match, like if he knew Alice's starting state and his bits don't match, then he knows that there's somebody in the middle listening, because the spy is collapsing the superposition and he can't recreate it. So that's the way that I'm interpreting this example. So as a communication between Alice and Bob in its current state, not very useful. As a way of finding if someone's listening on your channel, if you're sending a lot of data through and you can verify that bits are getting flipped here and there, then you can kind of figure out, hey, someone's listening in. Does that make sense? And I actually made a copy. This was another thing where, again, I'm kind of frustrated with the way that superposition works, because this screenshot I have is actually one where a spy was detected. So in this case, Alice starts with a 0, doesn't actually change the value before sending it, and Bob reads a 1. And so, and Bob does the same thing that Alice did, which in this case is nothing. So the input side and the output side lines up that they did the same thing, but Bob got a different value than what Alice had sent. And so based on this, we know there's someone in the middle who collapsed my superposition and then tried to stick it back into superposition. Now, running this in the simulator was a lot of fun is not the right word. Oh, I caught a spy on the first time. Because if we look, let's see, this one. So Alice did a not and a had, but Bob didn't do either of those on the other end. So his value doesn't match. So in this case, the spy read a 1, but Bob read a 0. And so looking at the code, this is the one place I'm going to look at the code, is kind of the very last section that says, here's how we know that there's a spy. So if the send had value, and this is a random, unfortunately, the circuit doesn't show it, but it's basically right here. Alice is deciding randomly, am I going to had this before I send it? And then Bob is doing the same thing on his end. but also chosen randomly. So this is saying if Alice's random choice and Bob's random choice match, that's the first thing we have to check. The next thing we have to check is whether the value Alice sent matches the value that Bob received. So if they're doing the same thing at the top, or Alice is doing the same thing before sending it and Bob is doing the same thing after he receives it, but the values don't match, then we know someone's tampered with it in the middle. So what are other people's thoughts on this? Because I'm going to stop now.
Sure, I'm going to just share this. No, actually you did great. I think we're all confused. I'm going to share my screen
Okay,
if I can.
let me
Can you
stop.
let me? Yeah,
I
just to show, yeah, go ahead. If I can share, you have to turn it on.
all participants can share there. I thought I did
so,
that at the beginning.
So, okay, no big deal. Okay, so the first thing is, let me just get this off. The first thing that I did, because it was bugging me, is I just kind of like refactored the code because I wanted to get a sense of it. So like the original code is here, right? And it had all these like extra things for formatting, all these labels and no-ops and everything. So I just kind of took all that off and I threw this up in my GitHub up here. So I've got all the code up here if you want to grab what I'm using. So the first thing is I got rid of all that. And I kind of just, I was trying to just manipulate it. So I changed the names, I changed the labels, and I just wanted to basically make it a little bit more compact. And then the big thing for me is I wanted to know like what was the outcome if you didn't catch a spy? Because I always want to see, like, I don't want to see nothing. So this is like a really small thing, but it just makes me feel better to understand what's going on. So just a little tweak that I added. So when I go ahead and
Can I make a comment on that?
yeah, sure.
Well, it's technically not accurate. It's more didn't catch a spy, because somebody's listening, you just don't know it in that state.
Well, and that's why I'm actually just embarrassing myself here, because that was the way I understood it. I wasn't really sure. So the more accurate thing would be, instead of kept a secret, it would be didn't catch a spy, right?
Yeah.
Yeah. So didn't would be the more accurate thing. So really, really small thing. So as I was going along, the idea that sometimes Alice would do this.
Excuse me. Would you mind going back? I think there's something with your code.
Yeah, here.
Oh, okay. No, sorry.
Yeah, no big deal.
With
So
the didn't part. Sorry. Isn't there an error there?
That it's the single quote.
It's the
the apostrophe is, yeah, that's messing up the stream.
here did not. There. Okay. Yeah. Okay, thanks. Anyway, so what I liked about this was if I just run this a few times, you can see here she didn't use these operations and he did do the had. And see how it just like collapses? It's a small thing, but by getting rid of the labels, I was able to see it more clearly. Does it make sense? To see when Alice is doing the had, when Betty, and I changed to Betty just for fun. And it was just by changing the labels. It allowed me to visualize what was happening better. Small thing. So the next thing, just really quickly, is I went and put this in the inspector, and where I really was able to see is on this line 31, and this is the QSAM code. So let me just set this back and set the breakpoint here. And the language is different, like Jeremy was saying. Like there's code in here that I don't know, like barrier. The other thing that's really interesting about this is this was helpful for me. You've got these qubits, but you have these sort of regular memory positions. You see it over here in the register? And that was like very helpful to me to see how this was being written. So here's the qubits, but here's not like regular memory positions where when you read, this is where it goes out. So this, the first week I was talking about decomposing the problems into the quantum portion and the classical portion. And this to me seems to be a really important part as we move along. So seeing that in this environment was really helpful. So
Yeah, I
anyway,
definitely see that because that's a piece that I was missing with the QC engine. Definitely,
yeah.
is
So-
those not qubits.
Yeah, and so then kind of just going, if I go to the beginning here and I go through, I can visualize this better when I look at the probabilities and this thing called the state vector and the Q sphere as I go through and look at it, even though the language is unfamiliar to me. That's more C-style language. And in particular, when you go to this decision point up here, and let me just reset it because I want to be respectful of time. And you go here and you're on this section of the code, which is this fiber, it's the barrier command, which again, I have to understand what's going on here. But the idea here is you've got 4 different possibilities, which again, this did not come through to me in this code. I don't see where you have the 4 different possibilities here. I'm honestly not done working on this problem. I don't feel like I understand it good enough, but this to me seems significant that at this choice point, you have 4 different possibilities because of the 2 qubits somewhere. And that is part of what this is testing for. So I'm sorry, and you can see here again, the circle notation. I'm sorry, I don't really have more the answer. I'm hoping that I just have more tools that can help us get to the answer. So with that, I will kind of pause there and see if anybody else has anything to share.
Lynn, were you able to get that to run in one of the environments or just within the composer?
I actually didn't do it yet. I was just inspecting it and I was trying to understand what the code did all the way across. But I will. But that 4 possibilities, I was like, what is this? I did not see 4 possibilities in the JavaScript environment. I only saw the yes or no.
Yeah, and I think it gets confusing because and again, that's something that is a chapter 3 thing.
You're comparing the qubit that it was transmitted, the bit, the checksum bit, or the whatever, the detectable. It's essentially saying, I'm sending on occasion something unencrypted, right? The storyline is you're sending a whole bunch of stuff that's supposed to be secret. So in order to detect a spy, you send something that everybody can see, spy or not spy, but for which an outcome is known and agreed upon ahead of time. So you have an expected thing on the other side. And because of the mechanics of the quantum mechanics, at some point, if a spy coalesced it, if a spy collapsed it by reading it, then it would have changed likely, maybe at a 50% split, I don't know, depending on how we program the circuit. So you have the qubit coming in and the qubit coming out, and those are 2. So maybe that's the reason for 4, because you can have the 4 possibilities there.
Well, it seems to me that's the key to understanding this, is my point. That's why I pointed to it. I don't understand exactly, but I feel like once I can explain that, I can explain this example.
So the way that I interpreted it and the way that I messed around with the code was that like when I was looking at it, it was like, okay, so they're more or less deciding on a key kind of, but like that key is more or less random. And so I was like, all right, forget this random key bit and just pretend that they have a shared secret, right? So in their shared secret is doing the had. So both are doing the had, right? At the end. And like, and the part that like where I was really focusing on was the spy part, because if in quantum, the quantum wave function, for example, when you do a measurement, the wave function in quantum, the wave function breaks down and then you have a single point. So that's why you have wave and particles existing in quantum, but you can only, when you measure quantum things, they only show as particles to you, but Stardinger's, I can't say his name right, but like his whole thing is like every quantum is a wave, right? And that's what the wave function is of the universe or whatever is what Einstein called it. But so the idea behind that is that like if the spy were to read it, then it collapses the wave function. And so the spy then has to like guess what the key is. The secret key is in order to like hide his tracks. Otherwise, there's a chance that someone's gonna figure out that someone's been reading it. So that's the way I kind of like interpret it. So I just made both keys on both ends known by each user, and then I kind of played around with the code near the end where it was just like checking to see if the expected value changed, which means that somebody was listening, and then the spy on the spy side is kind of like guessing on the had, right? So so you have like a 50% chance as a spy to get, in this case, to get the key correct. And so that's kind of how I was looking at it. And I'm not really like 100% sure, but I was like, but now that I'm reading this stuff, and watching Jeremy click through the stuff, I didn't even realize you could do that, because I think I missed that in the last thing. And I was like, oh, so I see the bit, there's a line, and that's what that means. There's a bit here, the qubits here, and then the line shows how the qubits life. And then there's that transfer where it's like the feed is like the transmission. And then at some point the spy is trying to read the transmission. And so that kind of helped me also like interpret it a little better. But I think it's confusing because they're trying to, I think the authors of the book are like kind of purposely writing weird code so that you sit there and you're trying to like figure out what they're trying to say to you. Because like if you're thinking about encryption, especially like RSA or AES, there's always like there's a concept of some sort of key, right? Like I think in AES there's like, or even in JWT you have the concept of a signature, right? So if you can match the signature, then you know that something hasn't been tampered with. So cool. I was just trying to like try to translate it into something that makes sense to me.
Yeah. So I would propose this. I feel like we're not done with this problem, but we are done with time for this week. So I feel like we should start next week with any learnings we have, or throw them into the Slack. I'm going to still work on this because I don't feel like it's done. But a more compelling question that is not quantum is the person that was going to take chapter 3 is not here today. And so I'm wondering if anybody is interested in leading our discussion on chapter 3. Don't all volunteer at once.
Well, Lynn, funny you should say that, because before you joined, I was having conversation with Gerard.
Gerard, would you like to lead chapter 3?
I will be honored.
Oh,
Unless Nuri wants to take it.
So we're Nuri, because you're new to this, we're all learning together, and so we're just kind of stepping up to lead and really working as like almost like a college study group. Nobody here is an expert. We're just trying to learn together. Gerard, thank you very much. And great. So let's do that then.
Can I suggest though that we consider deferring it, since I think this is the basics. This is the walk before the run. We don't get another walk.
Well, that's why
creating a good mental a good mental picture of what had really is. There was some terms around here that I'm not quite sure I agree with or understand in the same way, in terms of the nature of these basic logical operation or basic.
Well, let's do this. Let's just try it, and we can always go slower. So let's try getting a start on chapter 3. Maybe it takes us 2 weeks. I mean, we're doing this for the love of it. We're not in a hurry. So we're all curious about this 2-4 question. So let's continue to work on it in Slack, share.
Yeah, I was just suggesting to do this for chapter 2. That it's somewhere where we're all saying, hey, we still want to work this problem. So let's work this problem.
I do think, though, having read the whole book twice now, that it does actually, but you say wow, but I don't know how much of it's in here. I would say that going further will actually be helpful. That's just my feeling. We can reassess at the end of next week, but I'm feeling like let's just take a look at 3, see how far we get, and then kind of regroup, because you know, it's one of those things that as things start to come together, sometimes some of the foundational stuff, at least for me, makes more sense. So anyway, so we are running over time. I want to thank everybody for joining. Welcome, Nuri, especially new to our group. And Gerard, are you going to just touch in with Jeremy to get the resources that you need, the slide deck, if you wish to have the slide deck or anything like that for next week? Is there anything that we
I
can
didn't
be
even
doing?
know that I could do that, but thank you for suggesting. So Jeremy, you and I were gonna dance.
Yeah, and I think Lynn has posted the slide deck on
Slack.
Slack
Yeah,
as
yeah,
far as the
Slack.
template.
yeah. So I'm going to stop the recording now too, because I think that
Okay.
we can do that.